And we are being recorded. So I want to start out doing something I would have liked to have done last week. This is part of your homework. So I'm going to extend the homework, obviously, so that you have time to do it. And what we're going to do is learn how to add gravitational forces together to figure out what the net gravitational force is. This is called a vector. An example of a vector would be, I'm going 55 miles per hour east. And there's another concept called scalar. And a scalar is just saying, I'm going 55 miles per hour without anything about the direction. Vectors carry information about both how much of something there is and also what direction it's pointing. And scalars only carry information about how much of something there is. Step out of the way for a moment. I'm going to try to make sure to do that every single time I write, but I'm not going to give you all very much time to copy things down because you can always freeze the screen. But I'm going to give a little bit of time because we do have 1, 2, 3 people here in class live. So before we worry about gravity being a vector in any way, shape, or form, let's just consider what a vector is. So vector is a line with an arrow. Remember your high school geometry, this is called it's called an RA line. So it's a ray, not a line. And it's possible to add rays together. And there's a very complicated, well, not very complicated, but somewhat tedious mathematical way to do this. Fortunately, there is also a graphical way to do it. And now I will show you what it is. All vectors. So this could be how far you're going on a map, like you're walking around San Francisco, and you go this way, then that way, then this way, then that way. The verbal description of how I put this together is I take each ray, and I move them. Connecting the tail of the new one to the tip of the previous one. It doesn't much matter what order I do this in. Let's say I use 1, 2, 3, 4. I'm I'm going to redraw these, keeping the length as close to the same as I can. So 1, 2, 3, 4. And there is the order that I picked them in. However, it didn't have to be this way. One, 2, 3, 4. So 1, 2, 3, 4. Like that. Wait, I messed something up. Pardon me. While I figure it out. Oh, right. So this is vector 1 that is used, 2, 3, and 4. The resultant total vector, all these things added together, is from the tail of the very first vector to the tip of the very last vector. Resultant is kind of a fancy word. So let's go with total. So let's see what the result looks like for both of these. Here is from here to here. And here is from here to here. In both cases, you start out in one location, and then the vectors all add up in such a way that you get a line just pointing to the right. So if we're thinking about this in terms of directions, I would have gone a little bit northeast, a little bit east, a little bit southwest, a little bit east. And the net result is I only went east after all of those vectors are added together. Same thing here, I go east, I go southwest, then I go northeast. The net result is that I end up in a spot that is just east of where I started. So now let's do a bunch of examples. And by let's, I mean, I'll do a bunch of examples, then I'll ask those who are online how they're feeling about this, and then you do a bunch of examples. So I partitioned this board into 4 parts. Each part of the board is going to have a different set of vectors in it. So I'm going to try to add these together. 1, 2, 3. And the resultant is from here to about here. You do not have to do these problems perfectly to get perfect credit on them. Just a sketch of approximately what's going on is perfectly adequate to me. Almost exactly the same problem. I've just flipped one of these vectors. So I'll choose this one is 1, this one is 2, this one is 3. 1, 2, 3. In this case, there is no total. If we were thinking about distance, then I'd end up right back where I started. And if you're thinking about the vectors as being gravitational forces, then the net gravitational forces would sum to nothing. This would be a place that you can hang out in without gravity pulling you, particularly one way or another. One, two, three, four. Add them together. 1, 2, 3, 4. And again, you end up right where you started. There is no total. And of course, I could have put this together in a way that's a little bit more familiar to shape by doing 1, 2, 3, 4. 1, 2, 3, and 4. So now we have square, whereas this looks like a strange upside down L. But either way, there is no total force. This is my first vector. This is the tip of my last vector. So no total. All these chalk colors showing up okay on the camera? Feel free to turn on your mic and say something at any point. As always, 1, 2, 3. 1, 2, 3. And the net from here to here. Of those who are here, does anybody want more examples or explanations before you try your hand with a couple of these yourself? All right, let's get cracking. Again, the board is partitioned. Now I'd like you to give adding these things together a try. Remember that at this point, it doesn't particularly matter where the vectors are. You can drag them around so that the tail of one connects to the tip of the next. And then you grab a new one and connect that tail to that tip, so on and so forth, until you're done. Just keep track of what your first and your last vector was so you can draw a line from the very first tail to the very last tip. Okay, because there are students here live, I'm going to set a timer for 2 minutes. And when I can find my cell phone, when that 2 minutes is up, I'll ask if that was adequate time for y'all to give us a try. Remember that anytime there's a question, you can switch on your audio and ask it, or type a question in the chat window. If you want me to know that a question's coming, and don't want me to move on to the next topic, hit period enter fast, and I will see that and know that I need to wait. All right. Was that long enough? I see no chat. I hear no voices. 1, 2, 3, 4. Kind of arbitrarily picked. Oh, I need to give myself more space. 1, 2, 3, 4. And here is the net. One, 2, 3, 4. And I'm going to have to draw over the vector number 3, sorry. And there is the net for this problem. One, 2, 3. 1, 2, 3. So these two essentially cancel each other out. And that's the net. 1, 2, 3, 4. And that's the net. Any questions, any comments? Anybody need me to go over this particular idea any more before we move on? It does not matter what order they go in. No, no indeed. I can choose any order. So let's change the order of these. One, 2, 3, and 4. 1, 2, 3, and 4. And there's the net. Same length, same direction within the drawing skills that I possess. Any more questions? Okay. So let's move on to what all this has to do with gravity. So we got a moon and a planet, and we're going to follow 2 of Newton's laws. One, equal and opposite forces. Actually, I guess we're just going to follow one of Newton's laws. That's all that's necessary at this point. So there's a force of gravity. And I now need to wish I made that shorter. And a force of gravity. As hard as the planet tugs on the moon is tugging on the planet. This is not just true in the relationship in between astronomical objects. All the pandemic weight I've added, I believe I weigh now about 190 pounds. So the Earth is pulling down on me with a force of 190 pounds, but I am also pulling up on the Earth with a force of 190 pounds. When I do this, by an infinitesimal amount, I'm dragging the Earth upwards. And by infinitesimal, I mean very infinitesimal. Indeed, if we were to gather all the people together, standing shoulder to shoulder on one part of the planet, and they were all to jump at once, nothing would happen, at least not to the Earth. Okay, so that's the first key idea, that when an object pulls on another object, that other object pulls equally back on the first object. So the direction of the vector is always going to be from the center of one of the objects towards the center of the other object. But how long is the vector going to be? And there's two rules you've got to learn in order to estimate about the size of the vector in relationship to other vectors. Rule number one, the more mass, the stronger the force of gravity. Rule two, the greater the distance in between the objects, the weaker the force of gravity. So that's basically it. Rule one, rule two. Let me put these into practice so that they can be more sensible. I'm interested in that object. And I'll say this object has a mass m. And over here, there's an object with a mass of 2m. That's a distance d away. And over here, there's an object with a mass of just m. That's a distance also d away. So this object is going to experience a gravitational force, and it's going to experience a bigger gravitational force that way. I want to know what the net force on this object is, so I'm going to label this vector 1, is vector 2, and then I'm going to follow my addition rules. And so now I know what the net force on the planet is. And so I know which way the planet's going to move. Now, of course, because these are two separate forces, there's also force pairs. So this planet's being dragged towards the object of interest as hard as the object of interest is dragging the planet. And this planet is being dragged towards the object of interest as hard as the object of interest is being drawn towards that planet. But I don't have to worry about the force pairs because I'm trying to figure out what the net force is on the object of interest. Okay. Now let's do a problem where the distances are different, but the masses are the same. So now this is my object of interest. And this planet is 1.5 distances away. I don't know what the units of distances are. Could be astronomical units, could be light years, could be anything really. And this is just 1D away. So there's very precise mathematical laws that cover all this, but you're not in a position where you have to learn them. What you have to learn is this force is littler than this force. And I don't care how long the vectors are. I wouldn't grade you on that. What I'm going to grade you on is that this vector is longer than this vector. That's what I'm looking for. So that I know that you understand that a closer an object of similar masses, or the further an object of similar masses, affects the strength. So I will take vector 1, vector 2, vector 1 goes that way, vector 2 goes that way, and the net is this. So this object is being dragged by a net force mostly this way. And planets affect each other like this all the time. This is why the Earth's orbit goes from being mostly circular to mostly elliptical to mostly circular to mostly elliptical. And there's been times in the solar system where planets have moved around a really considerable amount relative to their orbits today. And fortunately, all the planets nowadays seem to have arrived at really stable orbits where they aren't tugging on each other strongly enough to knock each other out of their current orbit. I'm particularly grateful that Earth is in these circumstances. Let's do 4 examples, and then I will ask you to do 4 examples if there are no questions or clarifications. Now, quick note on these problems, just because I care about the concepts and not so much about the complexity. If there's a problem where the distances are different, the masses are going to be the same. If there's a problem where the masses are different, the distances are going to be the same. I'm not going to change 2 things on you at the same time. So, M, object of interest, 2M, everything's separated by the same distance. So a bigger force this way than this way. Take vector 1, take vector 2. And that is here. Consequently, I know this planet's being dragged roughly this direction. Here's my object of interest. All these distances are the same. So I've got strong force this way, a weaker force this way, and a weaker force even than that this way. So 1, 2, 3. 1, 2, 3. And the net is from here to here. So that's the way this planet's being dragged. Now I'll do 2 example problems where the distances are different. This distance is 3D. Here's my object of interest. And this distance is just D. Since the distances are different, the masses will always be the same. So weaker force this way, stronger force this way. I want to add them together. I get a net force that looks like this. So the planet's overall being dragged downward from the point of view of the board. So now I've got kind of a weird situation. There's 2 planets roughly in a row relative to our object of interest. Jupiter and Saturn just did this from the Earth's perspective. So I know the vector going from here to this mass is going to be quite a bit bigger than the vector going from here to this mass. And the vector going down towards this mass should be as big as that vector. 1, 2, 3. 1, 2, 3. And that's the net. This planet's being dragged that way. Questions before you try this on your own? Okay. Remember, I'm glancing at the chat screen every time I go over that away, and anybody is welcome to turn their mic on at any time. Go for it. I will again give you 2 minutes to give this thing a shot. Was that an adequate amount of time, or does anybody need more? All right. Pretty weak force, much stronger force. 1, 2. And the net is that away. So of course, this planet being dragged towards the object of equal mass is closer. Pretty weak force, much stronger force. 1, 2. And the net is from the tail of the very first one to the tip of the very last one. And since the distances are equal, yeah, this object is being dragged more towards the massive planet than towards the less massive planet. Oops. Trying to be more consistent with my chalk colors. This force and this force should be the same. And this force should be far weaker than this force. And that is how you figure out how strong gravitational forces are, give or take, and add them together graphically. Let's do another couple of examples. All right, this one is probably not helpful, but let's go ahead. The figure below shows several objects of different masses located on the surface of the Earth, which experiences greatest to least gravitational force. So that's DVCA. And then rank from greatest to least the gravitational force exerted on the Earth to each of these objects. Again, that's DVCA. on to a much more interesting question. So there's an astronaut standing at point A, point D, point C, and point B. I'd like you to take a moment and figure out what the gravitational forces on the astronaut will be from each object, or from each sets of asteroids. Then add them together graphically and figure out in what spot would the gravitational force be greatest and in what spot would the gravitational force be less. So this problem looks different than the problems that I have been demonstrating to you that you have been doing. But if you look under the hood, it's actually the same problem. So I have A, B, C, and, oh, sorry, A, D, C, and B. So the closer you are to an object, stronger the gravity. And the masses of these two things are the same. So for A, I've got a strong gravitational force coming from this asteroid, and I have a weaker gravitational force coming from that asteroid. For D, I've got a strong gravitational force coming from this asteroid, and a weaker gravitational force coming from that asteroid, because it's further away. For C, I've got a strong gravitational force coming from this asteroid, and a weaker gravitational force from this asteroid. And B has a strong gravitational force associated with this asteroid, and a weaker gravitational force coming from the other asteroid. So let's just add them and see which has the greatest and which has the least. So the net vector is the one in orange, and this is clearly the longest. C, this one goes with C, put it a little far away. C is clearly the least, and then D and B are kind of a toss-up. I don't know. The way I drew it, it looks like B might be a little bit bigger than D. But anyway, for sure, from greater, we have A, we'll say B, D. I would not take any points off if you said A, D, B, by the way. And then C for weakest. Questions over any of this? All right, that was our review of gravity. Now we're going to start a new unit. Unlike. So the element of the day is helium. Helium is super useful for making things cold. Really useful for making things cold. Certain medical instruments rely on a rare isotope of helium called helium-3 to even work. You can't build an MRI machine without access to helium-3. So I would ask you, please don't put it in balloons. Every drop of helium on this planet is precious. At least it is if you eventually need like your brain scan. Because once the helium leaks out of the balloon and is free in the atmosphere, it is so light that it will escape into outer space, the same way that oxygen escapes from Mars. You could dump a bunch of oxygen in the Martian atmosphere, but it would just leave. You could dump a bunch of helium in the Earth's atmosphere, but it'll just leave, going back to outer space. And we have no way to recover it, really. Helium was mostly created during the Big Bang, when the universe was about the right size to be a star from one end to another, if it even makes any sense to talk about the end of the universe, or the universe having sides. Astronomers kind of think that the universe is probably infinite, but we will never know for sure because the amount of the universe we can see is constantly shrinking due to something called dark energy that we're going to get to very late in the class. All new helium comes from either stars fusing or something called alpha decay. And most of the helium we have on Earth comes from alpha decay. And the way that works is that a bunch of the rocks in Earth's surface are radioactive. And so they spit out alpha particles, and alpha particles, that's alpha, by the way, are basically just helium nucleuses. So when we dig under the ground for pockets of natural gas, the rocks surrounding the natural gas are often radioactive. So rocks have been spitting out these helium nucleuses the entire time, and the container that the natural gas is in, bordered by all these rocks, is sufficiently non-porous that the helium stays trapped. So almost all the helium we get in the world, we get from pumping down, extracting natural gas, and it just so happens that a bunch of helium comes with it. So there's only really two countries in the world that have vast quantities of natural gas and pump it up. One of them is the US, the other one is Zimbabwe. And these are the only two sources of helium on the planet that we know of. And yet we put it in birthday balloons. I'd rather we not. But everybody makes their own choices about stuff like that. In this unit, we're going to talk about light. I'm going to introduce the idea of spectroscopy, and we're going to go back to it again and again and again, because it's very important to astronomy. And I'm going to discuss what the Doppler shift is and try to make that intuitive for you and easy to understand and apply. And then finally, I'm going to introduce the idea of black body radiation, which is another thing we're going to return to a lot. So nearly everything we know about astronomy comes from the study of light. There's three different ways that light can interact with matter. Matter can emit light, matter can absorb light, or matter can bounce light off of it. It can reflect light. And I encourage you all to go and play around with Zen Photon. It will really help you get an understanding of what emission, reflection, and absorption are. However, I'm not going to take the time in class to do that for you. But it's fun and it's really pretty. So I encourage you to do it, both to further your understanding and to have a good time for 10 minutes. So this is going to sound borderline impossible, but by the end of this class, I would like to convince you that by studying light, astronomers can figure out how hot something is, how fast it's moving, how far away it is, and most improbably, what chemicals it is made of, or what elements are inside of it. So what do you know about light? Normally we would brainstorm this and I'd write down a bunch of stuff on the board, but since there's only 3 people here, I'm just going to move on to what I know about light. Light is a thing that carries energy from one place to another. When an object emits light, it's giving away energy. When an object absorbs light, it's taking in energy. And when an object reflects light, it is sending the energy in a new direction. Light travels very fast, but not infinitely fast. And light is both a particle and a wave. So the person that figured out that light does not travel infinitely fast is an astronomer named, I apologize for butchering his name, Ultraviolet. And this is how he did it. So by this point, Newton's laws were very well understood. We knew how the moons of Jupiter traveled around Jupiter, and we knew pretty much exactly how fast they were moving. So this very careful astronomer figured out that when the Earth is on the far side of the sun from Jupiter, it takes an additional about, what is it? It takes an additional 16 minutes for the light to arrive from the moons. And so we're seeing Jupiter's moons delayed by their arrival time by 16 minutes. Knowing that, let us figure out how fast light is traveling. And the answer is from one side of the Earth's orbit to the other side of the Earth's orbit. You calculate the distance, and then you divide that by 16 minutes and 40 seconds. Velocity is, after all, distance divided by time. So the modern value for the speed of light is 3 × 10⁸ million meters per second. That's 300 million meters per second. Or in more familiar imperial units, it's 186,000 miles per hour. So pretty fast, but not infinitely fast. And so if the sun exploded, it would take us about 8.3 minutes to find out about it, because information, shock waves, gravity, nothing travels faster than the speed of light. And so if the sun vanished for 8.3 minutes, the Earth would continue orbiting around where the sun used to be. And then after that, we fly off in a straight line because there'd no longer be a huge object exerting a gravitational force on us. And then let's consider the time that light takes to travel from the sun to the nearest star, which is Proxima Centauri. That would take light 4.2 years. So this is why you'll hear people talk about astronomers looking into the past. We don't see Proxima Centauri as it is now. We see Proxima Centauri as it was 4.2 years ago. One consequence of this that astronomers make good use of is that the further away you look, the further back in time you look. This is how we know what the very earliest galaxies in the universe look like. Because if we just look at the very limit of the observational capabilities of our telescopes, we're seeing very far back in time indeed. So just a guess from y'all about how long would it take light to travel from one end of the Milky Way galaxy to the other. You know that kind of an average distance between stars is 4.2 light years. So the answer is that it would take you 100,000 years worth of traveling at the speed of light in order to get from one side of the Milky Way clear all the way over to the other side of the Milky Way. It's a big distance. This is why, even though our sun's old, billions of years old, about 5 billion, give or take, it's only been around the Milky Way a couple of dozen times. So it takes us a long time to orbit the center of the galaxy. So because light is so fast, it covers vast distances in a relatively short amount of time, but distances are so vast when you're dealing with outer space that it really does take you a long time for light to get from one end to another when you're considering scales on galactic scales. And then the distance in between galaxies would be even greater. So this is why astronomers talk about these large distances in terms of the time that light takes to travel that distance. A light year is a distance that light travels in 1 year, and that is a number that is absolutely nonsensical. So this is why we use scientific notation. If I were to write that number down on the board, I would be writing down 13 different separate numbers in order to totally express it. Whereas you can simply say 9.46 times 10 to the 15th and convey the same data. Okay, so I'm not going to have the people here do this activity, but I'd really like for you to pause this and do it at home, possibly by being on Google Hangouts with other people from the class, if you happen to know them. So if you could travel 1,000 miles for 1 cent, how much would it cost you to go around the Earth, around the Moon, to the Sun, or to Proxima Centauri? So pause the video, pull out your phones, figure it out. The answers are that it would take you about 25 cents to go around Earth, about $2.40 to go to the Moon, about $930 to go to the Sun. But if you were going to go to Proxima Centauri, it would take you $260 million. So distances at a certain point become meaningless, but money, you've got a good idea what money is. So lots of people have enough money in their checking account to get to the Sun at that rate, but you would have to be a quarter of the way to having $1 billion in order to get to Proxima Centauri. This is an extremely cheap rate too. You can travel 1,000 miles for 1 cent. Pretty good deal. Two mnemonics I'd like you to learn. Roy G. Biv and Raging Monsters Invaded Venus Using X-ray Guns. I'll tell you what each of these is about. R is red, O is orange, Y is yellow, G is green, V is blue, I is indigo, and B is violet, which is a color that Newton just kind of made up because he wanted there to be 1, 2, 3, 4, 5, 6, 7 of these. Like the 7 objects that were visible in the night sky and the 7 days of the week, which we get because there are 7 objects visible in the night sky, and so on and so forth. So this is the colors of the visual spectrum, which is a tiny little part of what light is. And this is the least energetic color of visible light. And this is the most energetic. So it really is true that red light will have less of an effect on a system than violet light will. But because this is such a small range, it's not like violet light is dangerous to you and red light is safe. Because the difference between red and violet, not so great. Now let's talk about rampaging monsters invaded Venus using X-ray guns. R is radio, a kind of light. M is microwave, a kind of light. I is infrared, a kind of light. V is visible, which is generally the only thing we think of as being light, but all these other things are in the club. U is ultraviolet. X is X-rays. And G is gamma rays. So I'm just going to talk about what each of these are. I typically write them on the board and solicit student interaction. You tell me some things you know about these, but hard to do that over Zoom. So radio waves are mainly used to communicate information on this planet. They are largely non-interactive. Notice, or with typical sized objects, they're largely non-interactive. Notice your cell phone works indoors. That's because radio waves can go right through a wall, typically. My cell phone doesn't work in here, but that's just because there's meters worth of stuff in between me and the outside world where there's cell phone towers. But cell phones send radio signals to convey information. M is microwave. So microwave is a pretty big range of light, but it does one thing that we particularly think of it as doing, which is that it'll heat up food. Now, this is a particular kind of microwave light, and not every type of microwave light will do this, but there's one very special band of microwave light that will take the water in your food and it'll basically make it go like this. This is why you can't put dehydrated things in a microwave oven. I mean, you can, it'll hurt your oven, but the food won't heat up. The microwave oven is heating the water inside of food, and that's pretty much its function. Then infrared light. So all things that have energy, and by energy in this context, I mean heat, everything that's warm emits some form of light. Infrared happens to be the kind of light that humans emit the most of. We also emit some microwave light and we emit some radial light. Fortunately, unless something terrible has happened, we do not emit visible light. If you're going to glow because you're hot, you've got to get up to around 3000 Kelvin or 3300 Celsius before you start glowing in visible light. And I don't know what that is in Fahrenheit, but it's definitely a temperature at which your body would be melting. Visible light, we see that, very convenient. Ultraviolet light. So our atmosphere mainly blocks ultraviolet light, which is a good thing because now light is getting energetic enough that it can hurt you. A little bit of ultraviolet light from the sun does make it through the Earth's atmosphere. And this has an effect on your body. Exposed to ultraviolet light in your skin in general says to itself, oh, I would not like to get skin cancer. I'm going to react by producing additional melanin and your skin will darken, provided you're exposed to ultraviolet light over a long enough time scale. Now, if you're exposed to a lot of ultraviolet light in a hurry, your skin won't have time to do that. So it'll just die. You'll get a sunburn, and then the skin will flake off of your body because it's dead and it's just not being held on very strongly anymore. So ultraviolet light is the most dangerous kind of light that we typically interact with. X-rays I use in hospitals, right? X-rays are such an energetic type of light that they will punch straight through your body, but metal will stop them. So there is metal in your bones, primarily calcium. And so the bones will block the light and you get a kind of a image of what your bone structure is, be it teeth or your leg or whatever it is you're interested in. The tiny amount of X-ray radiation you're exposed to when you get an X-ray in a hospital, not so big, but you really don't want to be around it a lot. This is my Dosimeter Ring. It's got a little piece of film in it. In 6 months, somebody from UC Berkeley will come and collect this ring and develop the film. And if the film has been largely exposed, then they will know that I have, at some point, a time while wearing the ring, been exposed to a huge amount of radiation, and everybody will get very alarmed, or at least I will. And then gamma rays. We don't use gamma rays for too much on Earth. It's possible for us to create them. It takes a lot of energy. The only typical use of them that I know of is cancer treatment. So cancer is what happens when part of your body decides that it's not going to die anymore. And so normally cells experience something called apoptosis or apotheosis. It's a word I've only ever read, so I'm not sure how to say it. But it basically just means cell death. Cells are programmed to die when their time comes. Cancer cells don't do that. So they just grow and grow and grow inside of your body. And eventually they push your organs out of the way and you perish. It's called cancer because when you do an autopsy on somebody that had cancer, you will see these veins and arteries just riddling where the cancer is because it's such a dense thing that it's demanding an enormous amount of your blood. So when you have cancer, there's actually a circumstance under which you want part of your body to die. You want your cancerous cells to die. If you're in a situation where it's feasible to use this kind of treatment, one thing that might happen is your doctor will suggest that they will beam some gamma rays through your body in the areas that cancer is. It's enormously dangerous. It might give you a mutation, but you already have a mutation. You have cancer. So it's probably worth the gamble. All right. Most of these are fortunately blocked. There are two clear windows that get through all the way through in Earth's atmosphere. One of which is visible light, which is why we evolved the capacity to see visible light. If visible light was completely blocked by the Earth's atmosphere, we would have evolved to see some other wavelength that's more optimal. And there are some animals that do see a little bit into the infrared or into the ultraviolet, so it's definitely possible for an eye to develop that can perform that kind of thing. And the other big window we have is radial waves. So radio telescopes and optical telescopes can be put on Earth and they work pretty well. Almost every other type of telescope has got to be in orbit. This is why we have all these space telescopes. Because if you want to analyze gamma rays, you can't do it from the surface of the Earth. It just doesn't work. Gamma rays are so energetic that they'll hit something in the atmosphere and that thing will explode, and that's the end of the gamma ray, far before it reaches the surface of the Earth. Different wavelengths are blocked by different reasons. For example, infrared light is mainly blocked by the water in the Earth's atmosphere. And as you can see, ultraviolet light is not completely blocked. The part of ultraviolet light that's very near visible light can make it to the surface. Hence, as we previously discussed, sunburns. So there's a bunch of space telescopes that look at all kinds of different wavelengths of light. Notice that there's also a plane on that, because sometimes you stick a telescope on a plane and fly it up real high and try to get some data that way. And you'll excuse me, I hear a sound from another classroom, which is the kind of thing that I've got to investigate here. So I shall be right back. Okay, sorry for the interruption. All is well at Cal. Moving forward. So biggest takeaway, only radio light and visible light makes it to the Earth's surface. You can play some complicated tricks and kind of get at some of the other types of light. For example, you can choose particularly high and dry mountains and get some data out of that. Got a bunch of microwave telescopes on top of the Andes, for example. But they still don't work as well as if they were just flat out in outer space. Here's the X-ray image of the sky with the false color corresponding to the energeticness of visible light. So the part that you see as red is less energetic, a lot less energetic than the part that you see as violet. Interesting stuff. So the center of this picture is the center of the Milky Way. Notice there's a lot of bluish light in the center of the Milky Way. The center of our galaxy is a place that is fairly active in X-rays. One of the many, many, many reasons that it's good to live in the suburbs from the point of view of where your star is going to be in a galaxy. You don't want to be too close to the center. So is light a wave or a particle? And the answer is, weirdly, it's both. Sometimes light behaves like a wave, sometimes light behaves like a particle. And this is known as wave-particle duality. And it is a big part of quantum mechanics. So light can behave as a wave, and typically does when it's passing by an object, or it can behave like a particle, and that typically happens when it's absorbed by an object. All light is created by both electricity and magnetism. This isn't a physics class, so I'm not going to get too into this, but just to remind you, magnetic fields are the things that magnets have. Electric fields are the things that you pick up when you take your shoes off and shuffle across the carpet, or you go down a plastic slide at a playground. And you end up ever so slightly charged, and that charge is an electric field. And when you touch somebody, you shouldn't do, the excess charge on your body gets transferred to them, because charges do not like to hang around with each other if they're similar charges. Positives will do anything they can to get away from other positives. Negatives will do anything they can to get away from other negatives. This is also the reason why, if your car is struck by lightning, stay inside for a while, because the whole outer surface of the car has picked up a lot of charge. It hasn't gotten inside you because the charge would prefer to stay as far away as possible, which means it has distributed itself all around the outer surface of the car. But if you open the car door and put your foot on the ground, then you just created a path for that charge to get off of the surface of the car and into the ground, where the positive and negative charge can be much further away from each other. So that's what they like to do. So picture of a magnet. So this is light, and light is half an electric field, half a magnetic field. Enough said about that. Take physics class at some point, and there will be much more that is commented on it. So anytime you make a wave, you've got to have some kind of agitation. Could be drips of water falling on a still surface of water, or it could be taking a charge and shaking it, which is what creates light. So water droplets can create ripples on water, and shaking charges creates ripples, and those ripples are light. The faster you shake the charge, the more energetic kind of light that you make. This is why I say all things that are warm glow, because all things have charges inside of them. And if you're warm, those charges are shaking around inside of you. I'm 32 degrees centigrade, 98 degrees Fahrenheit, something like that, give or take. And that means that the atoms in my body are bouncing around with a certain amount of speed. And that speed is enough for me to generate infrared light, microwave light, and radio light. The surface of the sun is 6,000 degrees Kelvin, or 6,300 degrees centigrade, and I don't have any idea what it would be in Fahrenheit. So that's hot enough to make visible light. And of course, the sun also generates infrared light, microwave light, radio light, and a tiny little bit of ultraviolet light, unfortunately, if you want to avoid skin cancer. So only one of these outlets still works, but let me show it to you. This is how you make radio waves, or radial light waves. You have an antenna, you have electrons in the antenna, and you're shooting them up and down. So you're moving a charge. Moving a charge creates light. And in this instance, I'm moving the charge slowly enough that it's just creating radio light. And that light propagates out away from the antenna. And if it passes through another piece of metal, then that can cause the charges in the metal to oscillate backwards and forwards. This is what generates the signal that lets your car listen to radio, or lets your cell phone communicate with the cell phone towers, so on and so forth. So this ripple analogy breaks down with light somewhat because of this reason. If you're in a boat, you can outrun your own weight. You can make waves and move faster than those waves. You can't do that with light, because light is traveling at the maximum speed that anything can travel in the entire universe. You can't outrun the light ripples that you create. But you can with almost every other kind of wave. So I'm going to try not to use these words too much in this class, but formally, there's a vocabulary associated with all waves. So amplitude means how much of the wave there is. So if I have a dimmer on the lights in my house and I raise the slider and I make the lights brighter, I'm increasing the amplitude. Turn the slider down, make the lights dimmer, I'm decreasing the amplitude. Wavelength is a measure of size of a light wave. In general, the longer a light wave is, the less energetic it is. Radial waves are very long, about that long to infinitely long. Anything that's longer than this, we call radial. Let me step entirely in the field of the camera. Frequency is the number of wave crests passing it by a space per second. And in general, the higher the frequency, the more energetic light is. And the wave speed is how fast the wave travels, which for the speed of light is always 3.0 times 10 to the 8 meters per second. Or at least that's the answer we're going to give in astronomy class. So radial waves, huge wavelength, small frequency. Gamma rays, small wavelength, huge frequency. Now here's the words I'm going to actually try to use in this class. Rather than saying wavelength, I'm going to say size. These kinds of light rays are big. These kinds of light rays are small. And rather than say frequency, I'm just going to say energy. This kind of light is not very energetic. This kind of light is hugely energetic. Because we're more familiar with the words size and energetic than we are with the words frequency and wavelength. Okay, so wavelength is how big light is, and frequency is how energetic light is. When one goes up, the other goes down. So the most energetic light is the smallest, and the least energetic light is the biggest. More stuff about the electromagnetic spectrum. Because red light is less energetic than violet light, red light is bigger than violet light. And different colors of light move differently in things like glass or water, or really anything that's not vacuum. This is why a prism works, and it can separate out white light into a rainbow. And there's the entire electromagnetic spectrum. It's actually being written in terms of powers of 10, and so it's even bigger than it seems here. But notice how tiny the visible spectrum is in comparison to everything else. It's super tiny, and yet that's all we can see. So, like it is usually described as a wave when it travels through space, and light is usually described as a particle when it interacts with atoms. We are only looking at one circumstance under which light behaves like a particle, and that's something called the photoelectric effect. And it's relevant to astronomy because the photoelectric effect means basically this. When light that is energetic enough hits a metal, it'll make charges fly off the metal. This is how solar power works. You have solar rays on your roof. Sunlight is striking those, and it's making charges become energetic, and then you hook a wire up to it and run your blender, and then return the charges back to the photocell when you're done using their energy. But what this means for space exploration is that when you've got a satellite or a spaceship or whatever, it's probably going to have to be made out of metal. And that means that one side of the satellite is always going to be charged. The side facing the sun is going to be picking up a little bit of a charge as the sunlight strikes the metal. The side facing away from the sun, not going to be charged. This is actually a significant engineering problem. It's something that you've got to think about every single time you shoot something in space. So not all kinds of light will make charges fly off. So for potassium, which is actually a metal that's pretty easy to get electrons to fly off of, red light won't do it at all. Green light will make a little bit of current fly off. And violet light will make a similar amount of current fly off, but it'll give it a lot more energy. So let's delve into quantum mechanics for just a moment. In middle school, we're taught to think of electrons as orbiting around the center of the nucleus, kind of the same way that the planets orbit the sun. That's not what quantum mechanics say. Quantum mechanics say that electrons are located in a kind of cloud of probability around the nucleus. And they're held in place by electric force. The nucleus is got a bunch of positive things in it. The electrons are negative things. Negative things like to hang out next to positive things. And so the electrons stick around unless it becomes so hot they're knocked off, which happens sometimes, especially in astronomy where things can get extremely hot. So, quick question, go ahead and pause. This is an example of the kind of question that I will ask on quizzes, and you all are actually due for your first quiz, but I won't give it until next Monday. What phase of the moon is it best to go out for low tide? Is it full moon, new moon, half moon, or full and new moon? And the answer happens to be, remember, pause, think about it. The answer happens to be B. So all atoms are important to astronomy, but some atoms are vastly more important than others. The most common type of atom in the universe, by a long shot, is hydrogen. Hydrogen is what matter will turn into when the universe cools enough to allow matter to exist. And so you can imagine that in the original Big Bang, there was like this primordial, super hot, unbelievably hot thing going on. But as it expanded and cooled, eventually got cool enough that instead of just being intense energy that would just blast anything apart in an instant, it cools enough that matter can actually exist. And the kind of matter you get naturally is hydrogen. Now, all of these things are hydrogen, but the thing labeled as deuterium has a neutron, and most hydrogen doesn't. And the thing labeled as tritium has 2 neutrons, and most hydrogen definitely doesn't have 2 neutrons. This changes the weight of the atom, but it doesn't really change its chemical properties at all. The nucleus is tiny. When we feel something from an atom, or when an atom chemically combines with something else, it's the electron that does almost all of the interaction, because the electron's on the outside. And all 3 of these things only have 1 positive charge on the inside. That's what makes it hydrogen. Consequently, it can only attract 1 electron. So all 3 of these only have 1 electron. Consequently, they behave chemically almost exactly the same way. These 2 isotopes of hydrogen, deuterium and tritium, pretty much exist because the universe grows out of being a star. Remember that at a certain point in the Big Bang, the universe was hot enough that it was basically, hey, Terry, question? All right, I'm recording lecture, sorry. The universe was hot enough that it was basically a star for its entire existence, from one, again, and this is really the right word to use, but from one end of the universe to another end of the universe, it was solid star. There was nothing besides a star. Now, any normal star will make deuterium and tritium, but it also consumes it. Like it's gonna take the deuterium and tritium and it's gonna build hydrogen out of it. But because the star that was the universe just turned off, a lot of processes were interrupted halfway. Consequently, this universe star left behind a fair amount of deuterium and a fair amount of tritium. And that's pretty much where all of our deuterium and tritium come from. Is the Big Bang being a star and then suddenly not being a star. So electrons are things on the outside, they've got a negative charge. Protons are the things in the nucleus that have positive charge. And the things in the nucleus that have no charge are called neutrons. The electrons are located in a kind of a probability cloud around the nucleus, held in place by the attraction of the electric force. The number of protons determines what atom it is. If it's hydrogen, it's got 1 proton. If it's helium, it's got 2 protons. If it's lithium, it's got 3 protons. If it's uranium, it's got 92 protons, so on and so forth. And the number of neutrons affects what isotope it is, but it doesn't change the chemical properties at all. And then there's the big old periodic table of elements. So hafnium has 72 protons, yttrium has 39 protons, so on and so forth. Just look at the number in the upper left-hand corner, and that's how many protons it's going to have, and that's also how many electrons it's going to have, as long as none of the electrons are knocked off. And again, they can be if it's hot enough. But if a proton's knocked off, then you no longer have the same atom as you had previously. So the number of protons determines what atom you are, and the more protons you have, the more and more neutrons you need to add to make the core stable. And you can kind of imagine why. Positive charges want to get away from other positive charges. They repulse each other. Now there is something that holds the nucleus together. It's called, uncreatively, the strong nuclear force. And it's real strong, but it's not so strong that the force of repulsion between the protons is meaningless. And so you have to add more neutrons in order to make the strong nuclear force stronger and stronger and stronger. So at an element like carbon, that's what is the molecular backbone for life, more or less. You're going to have 8. Yeah, 8. Let me double check actually real quick. I'm not a chemist. No, you're going to have 6. You're going to have 6 protons and 6 neutrons, and that kind of balances out with. But with an element like uranium, you have 92 protons, but you've got to have about 238 neutrons in order to keep the nucleus stable. So 92 protons, 238 neutrons. Now the isotope of uranium that we use to make nuclear weapons only has 235 neutrons. That's why it's uranium-235. And that is less stable, so it's easier to get the nucleus to break apart and release a ton of energy when it doesn't. Now, electrons orbiting around a nucleus are kind of existing as if they're on rungs of a ladder. They would like to be on the lowest rung possible, because that's the most stable. That's the closest to the nucleus. That's where they feel the strongest force from the positive charge. It's just more stable that way. But every once in a while, they get hit by light, and the electron jumps further away from the nucleus, up to another rung of the ladder. When that happens, it would like to go back down. It's in an excited state. It would like to return to its ground state. And the way that it does that is that it spits out a beam of light. So it does. It just spits out a beam of light, and then it drops back to the ground state. Now, you make the electron jump up in energy, then it will immediately collapse. But if you give it enough energy, you can knock it clean off. And then we say that the atom is ionized. And that means that it's missing 1 electron relative to what it would have if it were just stable. And this happens quite often to atoms when it's extremely hot. So atom absorbs a photon, electron jumps up to a higher energy level. It will very quickly emit a photon, and the electron will jump back down to the lowest energy level it can possibly be in. And that photon has a really specific color to it, like perfectly specific. So let's look at a cloud of gas that's hot. Because the gases bumping into each other, the electrons are occasionally being forced into a higher energy state, and then they drop back down. In this case, they're emitting green light. Now, the size of the green light that's emitted by this gas cloud is really specific. And we can figure out exactly what element the gas cloud is made up of by analyzing that green light. So you send the light through a telescope. After that, you send the light through a prism, so the light will break up. And then you see exactly what wavelength of light you're dealing with. And each chemical element, and each molecule actually, which is just a bunch of elements stuck together, has a really specific light fingerprint that it gives out. So once astronomers observe that light fingerprint, they know what elements something is made up of. So here's what hydrogen does. And hydrogen can be knocked up to a bunch of different energy states, and then it'll fall back down. The Balmer series is just the only one that we can see. That's when it emits visible light. And the Lyman series emits ultraviolet light, and the Paschen series emits infrared light, neither of which is observable by humans. But look at the colors. Red, green, and blue are all colors it emits. When your eye sees those colors and averages them together, you get a kind of a pink. It really looks pink. This is why when you go by a neon sign and it's pink, what's actually in that little glass tube is hydrogen gas. It's being excited. Now, so hydrogen gas makes a pinkish color. Mercury vapor that's been electrified makes a bluish color. Neon vapor that's been electrified makes a really bright red color. So on and so forth. And this is an example of a different kind of way to make light. So in this case, this light isn't being created because things are hot. I mean, we're having to run a current through the neon side in order to make the electrons jump around like this. But the temperature doesn't have to be super high. Instead, the light is being created by the electron jumping up and then falling back down. But still, the method by which the light is generated is the same. A charge is moved up, and then a charge moves down. In order to generate all light, you've got to take a charge and shake it. So there's what hydrogen gas looks like as you shine it through a prism. And here's what a bunch of different optical signatures look like for a bunch of different gases, all of which you can see just walking around in any city, in open signs or in software advertisements or whatever. So hydrogen, helium, neon, sodium, and mercury, all in common use. Mercury is in particularly common use because mercury generates a bunch of ultraviolet light. So a naked mercury gas will look pretty darn blue, but you can put a little coating around it, and that coating can absorb the ultraviolet light, and then it re-emits white light, white-ish light. So that's what's in the lights in this room, and that's what's in the curly cube light bulbs you can buy. And that's the reason why when you break one of those, I believe they're called CFT bulbs, you should leave the house. Like you just broke a bulb with a bunch of mercury in it. And it's also the reason why you shouldn't throw them in the trash, because you're throwing something in the trash that contains a bunch of mercury. And trash bags tend to break. So different types of spectrum. You can have continuous spectrum, where that's the kind of light you get just from things being hot. And you have every different color of light represented there because the atoms inside of the body that's generating the light are all moving at different speeds. You can also have light coming from a hot gas, and then you get an emission spectrum. Or, right, this page is no longer relevant because I'm not doing in-person instruction. Or you can have something that's being generated through heat. So continuous spectrum, like the sort of light the star will create. And that starlight can pass through a cool gas. And then instead of seeing an emission spectrum, we see those colors of light missing. And that's called an absorption spectrum. And this is a big part of how astronomers figure out what kinds of things are out there in the universe. For example, this is how we know what the atmosphere of some of the moons around Jupiter or Saturn are. We wait for a star to get blocked by the atmosphere of the moon. And then we just look at the light pattern that we can see as the starlight passes through the atmosphere of the moon, and we look at what the absorption spectrum is. So this is how we know that Titan has an atmosphere that has a lot of nitrogen in it, for example. Only other place in the solar system besides Earth that has a lot of nitrogen in its atmosphere. Earth is about 80% nitrogen by total mass in the atmosphere. So I can't give you diffraction gratings anymore. So another moot point. But they're the super simple device that you can use to just break light into a spectrum. Much, much, much easier than using a prism, what all modern astronomers use. So I'm going to give you a couple of examples here. This is an emission line spectrum, and here is a continuous spectrum. And the colors that are present at the top is an artist's attempt to show how bright the spectrum is in certain wavelengths. So with the object to the left, that's pretty straightforward. Each emission line is about equally bright. But for the object to the right, that's something that's emitting light because it's hot, but it's not emitting equally across every color of light. So blue is very strong, green is very strong, but it gets weaker as it gets to yellow, and then it gets weaker yet as it gets to red. So normally I would challenge a class to do this. Now I'd walk around and check out your work and offer all kinds of feedback, help point you in the right direction. But that's not going to happen in the era of remote learning. So let me close this so that we highlight the blackboard. Oh, but then that had the side effect that I can't see this anymore. Okay. So top left looks to me like it's about equally bright in every color. So I'll do that. Top right is a very strange thing. It seems to be kind of bright in blue, and then trails off, and it's kind of bright again in reddish, although not as bright. So I should make the second hump littler. And then this one seems to have the normal color patterns associated with something that's glowing because it's hot, but it also has a bunch of emission lines where the light is particularly strong. So that's something you can see in astronomy for sure. And this has a characteristic color pattern of something that's glowing because it's hot, but it's missing some lines, and that's an absorption pattern. So I don't know of anything in the universe that can generate a light pattern like this. Light that's equally bright in every color, it just doesn't exist. But I can speculate as to what this is. I think this is probably two stars in orbit around each other. This star is probably hotter but smaller because it's generating less light. And this star is cooler but bigger. This is just a hot star that's got a bunch of elements in it that have emission lines. And this is a star that's passing through a gas, or possibly just the light is passing through its own atmosphere, because stars do have atmospheres and the atmospheres cool off pretty quickly. You're getting these absorption lines from the light passing through different areas. And then here's a spectrum of a pretty simple star. So it's either got an atmosphere that's cool enough to absorb light, or else it's passing through a gas cloud somewhere. And so I'm not going to go into how, but by looking at the strength of the absorption lines and how broad they are, you can knock out information about temperature, pressure, and density of the region of the star containing that atom. So when we examine a spectrum of stars, we see that certain elements comprise 99.999% of stars, including the sun. So hydrogen, helium, carbon, nitrogen, oxygen, neon, and sulfur are vastly overrepresented. There's a good reason for that. These are elements that stars have an easy time making. Later on, the star explodes. Much later on, our sun forms, and it incorporates the exploded body of the previous stars. And here is a spectrum of the sun. Look how complicated that is. Wait, am I sharing the screen? It better be. Possibly I am not. And nobody on this call has any audio, but I'm not seeing any chats either. It's also possible that everybody's walked away from their computer and I'm speaking to nobody. So back to here, there's a normal spectrum of a star, kind of a simple star. There's the elements that comprise most of a star, including the sun. And there's a spectrum of a sun. So in general, we can look at a star and say how many supernovas it's incorporating in a spot. So I'm just looking at a star and see how many heavy elements, by heavy elements we mean anything that isn't hydrogen or helium, that are present in the surface of the star, and say, that star assembled itself using the body of 2 exploded supernovas, or 3 exploded supernovas. Our sun is so chemically complex that we don't have any idea how many supernovae it's absorbed into its body. A lot of supernovae. This is the one thing we're sure of. We don't know exactly how many. Okay. Thanks for the chat message. I guess you can see it the whole time. Now we're getting to the home stretch. We're going to do the Doppler effect. We're going to do black body radiation. Thank you for sticking with this. Those of you watching the recording or following along live. Here is an explanation of the Doppler effect, courtesy of YouTube. And then I'll go back and try to explain it in my own words. Apparently I did not get this video promoted.
This angle always 90 degrees. Here's a new way to learn math that's fun to learn. Really? You'll learn it. The Doppler effect. In shell words, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck, it could be a sound, it could be a star, light, it could be a duck creating a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that's emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you. And the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and it's to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves of this emitting bunch up. So they deliver to you at a high frequency, which you interpret as a higher pitch, because the frequency of sound waves is hit. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear it at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of say you look at your observatory and you see a star. Just like the sound waves, if the star is moving towards it, it's a little bit. The light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, see that the small change in frequency for visible light will change its color. Higher frequency light waves mean blue light, and lower frequency light waves mean red light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang, an indication that the Earth might get very low in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay. And this is why I pay for YouTube, but I guess I'm not logged into my own channel. Stop share. So here's the star. And it's yellow. If you're in orbit around it, it's yellow. Here's the Earth watching that star somewhere far away. So telescope, actually a huge telescope. Take the same star, send it towards Earth real fast, and it's blue. Take the same star, send it away from Earth real fast, and the star is seen by us to be red. So I should say this star is seen by us to be blue, this star is seen by us to be red. And this is a persistent real effect that astronomers see. And this is how we figure out, I'm trying to make this full screen. And this is how we figure out how fast a star is approaching us and how fast a star is moving away from us. You look at the spectrum. So in this case, we've got a spectrum of a star. If the star is moving towards the Earth, the absorption lines move to the left. If the star is moving the star is moving towards the Earth, the spectrum shifts to the left. Notice that there's really distinct patterns in the chemical composition of the star, and that's reflected in what lines are missing. And you can look at the relative spacing of what lines are missing to figure out what the original color was. And then you know how fast an object is moving towards us or away from us. The panels on the right show the emission lines of spectra from 5 identical stars. And the panel on the top shows the rest frame spectrum. The stars are moving. Which star is moving towards us the fastest? Go ahead and pause, look this over very carefully. And the answer is A. A is moving towards us the fastest. Now let's do a bunch more problems. So exercise 1. Rank the pitch of the horn from highest pitch to lowest pitch as heard by each person. So C is going to hear the highest pitch, B is going to hear the lowest pitch, and A is going to be somewhere in the middle. And then rank the size of the sound wave heard by each person. C is hearing a sound wave that's very small. B is hearing a sound wave that's much bigger, and A is hearing a sound wave that's in between. New problem. Go ahead and pause, really think about it. The figure below shows a motion of 5 different stars relative to a stationary observer, a telescope. Speed and direction of each star is indicated by the length and direction of the arrows shown. And there's something else you've got to know before you do this problem. Doppler shift only gives you information about the speed towards or away from the observer. So to continue with the example I had up here, there's a planet that's observing these stars. If this star was yellow and going this way, then we would still see that star as yellow because it's moving, but it's not moving towards us or away from us. And so only motion towards, only motion away actually affects the color and actually causes a Doppler shift. So now you can do this problem, pause, think it over. What is the Doppler shift from most blue shifted to most red shifted? And the answer is, we pause and thought it over. A, C, B, which has no red shifting or blue shifting. And then D is very slightly red shifted. And E is much more red shifted. One way that I like to phrase this problem on quizzes and stuff like that is to say, let's say the star is yellow. I give you a range of colors of what we could observe it as when it reaches the Earth. A would be bluish, C could be green, B would be still yellow, D would be orange, and E would be red. Now, keep in mind, a star would have to be moving really fast, implausibly fast, for its original color to have been yellow, and then us to see it as either being blue or red. But if possible, final question on the Doppler shift. Here is a lab spectra of some element, and then we see the observed lines at a bunch of different stars. Rank the size of the Doppler shift from largest to smallest from the light from each star. So B is most blue shifted, and then D, then E, C, A is barely shifted at all, but it's a little red shifted, and then C is the most red shifted. So the answer to this one would be, I have to look back at this. B is most blue shifted. DE AC. Another example of a type of question that's very commonly put on quizzes. Back to the presentation. So the temperature of an object is maintained by a balance in between heating and cooling. If temperatures of an object is roughly constant over time, we'd say that heating and cooling are balanced, and then the object is in thermal equilibrium. Many types of objects can be in thermal equilibrium. Our body is. Ideally, our planet is. The planet is taking in more light than it's putting out, then it's heating up. Planet's putting out more light than it's taking in, it's cooling down. Now, our planet is currently heating up because our atmosphere is opaque to infrared light. It blocks microwave light too. CO2 and a bunch of other greenhouse gases make it better at this job. But the atmosphere is completely transparent to visible light. So the light from the sun comes in, hits the Earth heats up, and then it shoots infrared light back towards the sky. But the sky just bounces that light back to the Earth. And the more effectively it bounces the light back to the Earth, the more our planet heats up. And that's global warming in a nutshell. In case you didn't believe me by this point that humans emit infrared light, let me take one more try at convincing you.
These days, we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms, or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when you look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light you're used to thinking about. The sun, for example, or star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all colors from violet to red. But there are actually lots of other kinds of light that are also insensitive. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. Blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radial waves, which can have wavelengths larger than the entire Earth. The kind of light an object emits depends on its temperature. We're used to thinking of something hot giving off light, but it might surprise you to learn that objects that are cooler, like myself, give off a kind of light too, and that's what a night vision camera can pick up. That sort of light is called infrared light. The world sure looks a lot different in infrared light. Remember that what you're actually seeing is temperature. Something that's warm is going to look bright in the infrared. And something that's cool looks dark. Ice cream. Goldberg. And infrared radiation is actually a function of temperature. Places on my face that are cold, like my nose, they're dark in infrared cameras, they're giving off less infrared radiation. And places that are warm, like my mouth, or the hair next to my head, are brighter because they're warmer. You can even see my breath and my nose if you look carefully. And this is an ice cube. Humans, of course, are not the only things that emit infrared light. What do you think we can learn about animals by observing them in infrared? What about reptiles? Remember the cold-blooded. Giraffes. Here's a Nubian ibex. What do you think horns look like in infrared? Can you even see a gorilla in this picture? If you look carefully, you'll notice you can still see the zebra stripes even in the infrared. How about elephants? Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just as infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. As you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with in the night sky. But now, let's look at it through an infrared camera. How much is this? Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. In the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope facility. And it should give us a whole new perspective on space.
Okay, so heat, temperature, light, we've covered a lot of this. Temperature is a measure of how fast the atoms in an object are moving or vibrating, or whatever you want to call it. Normal air molecules zoom around the room at about 100 miles per hour. Atoms inside solids are arranged in a lattice, and then they vibrate inside the lattice. Either way, important thing is that atoms have charges. Charges are being shook. Shook charges make light. The harder they're shook, the higher the energy light they make. So these random motions are called thermal motion, and energy associated with the motion is called thermal energy. Absolute zero is the point at which all atoms are completely still. This is not actually possible to achieve in real life, although scientists have come close to it in laboratories. You could reach absolute zero, and you would have an object that's emitting absolutely no light. And then probably Fahrenheit is the thing you're most familiar with. Fahrenheit is negative 459.57 at the point where you reach absolute zero. And Kelvin is the exact same scale as Celsius, only instead of starting with freezing water, it starts at absolute zero. So Kelvin is the unit for temperature that scientists usually use, and room temperature is around 300 Kelvin. Surface of the sun, around 6,000 Kelvin. Filament of a light bulb, I think around 2,000 Kelvin. So atoms jiggling charged particles produce light. Hotter something is, the more light it makes. So light bulb makes light because it's hot. This is incidentally why people talked about why incandescent light bulbs are so inefficient back in the day when we had incandescent light bulbs. It's because they're about 2,000 Kelvin, and most of the light they emit is infrared light. Only a tiny portion is visible, and so only a tiny portion of the energy they use outputs light we can actually see. Light bulbs are perfectly efficient at putting out light. They just our incandescent light bulbs are perfectly efficient at putting out light. They just mainly put out light of a sort that you can't observe. So there's something that's hot enough for the low invisible light, and notice how cautious the person working with it has to be. At a certain level of temperature, an object becomes so hot that it'll start to output mainly ultraviolet light. There's a lot of stars out there that are that hot. But let me ask you a follow-up question. If a star is mainly putting out ultraviolet light, is it also emitting visible light? And after you think about it for a second, the answer is yes. Because that curve showing what kind of light it outputs still includes visible light. Okay. All these curves are collectively called black body spectrum. The hotter something is, the more luminous it is. And we measure that in units of watts, just like the watts written on the top of your light bulb. Hotter objects are bluer, cooler objects are redder. There's some physics laws associated with this that you don't have to know at all. And you don't have to memorize this either, but just for your own information, luminosity goes as about T to the fourth. So that's temperature times temperature times temperature times temperature. That's a really strong relationship. So I have two light bulbs. One light bulb has a temperature of 1000 K. One light bulb has a temperature of 2000 K. Make a ratio. 2000 divided by 1000 is 2 to 1. And then you take that number 2, instead of squaring it, instead of cubing it, you raise it to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. So doubling the temperature makes an object 16 times more luminous. Now, notice I'm saying luminous as opposed to bright, which seems like it'd be another perfectly good word. But luminosity and brightness mean two different things to astronomers. So when I say luminosity, I'm talking about how much total light is put out by an object. When I say brightness, I'm talking about how bright an object seems to be to me. Let's take an example of a light bulb. I can walk so far away from the light bulb that I can't see it anymore. The closer I walk to the light bulb, the brighter it'll be. The light bulb has been putting out light at the same luminosity the entire time. Okay, believe it or not, the end is in sight. Let me show you what black bodies look like if you're able to crank the temperature up or down. Here's I did not get this loaded. So let's get it loaded. All right, here's about the black body spectrum that the sun puts out. So I'm going to crank the temperature way down. Right now we're at about 6,000 Kelvin. I'm going to take it down to the temperature of a light bulb. So this is a regular incandescent light bulb, the kind of light bulb that glows because it's hot. And indeed, most of the light that it's putting out is infrared. We go all the way down to the temperature of the Earth. First off, we can't see the spectrum anymore, so I'm going to have to zoom way in. And the Earth is, on this scale, barely emitting any light at all. And what light it is emitting is of an energy type that carbon dioxide, water vapor, and methane make it reflect back towards the Earth very efficiently. Now let's go look at some brighter things. So there's a light bulb. Zooming out so we can actually see it. Here's the sun, zooming out so we can actually see it. And here is a truly hot star. Sirius A is known as a dog star. So this is one of the stars that's so hot that it puts out mainly ultraviolet light. But it also puts out visible light and infrared light and every other kind of light that's lower energy than ultraviolet. It just puts out less of it. And notice, as I crank the temperature down, Sirius A still emits more visible light than the sun does. The sun peaks in visible light, peaks about at green, Our sun is greenish, but it does not emit nearly as much visible light as the truly hot stars. So Sirius A emits more of everything than the sun does. Now, I do not see the button to stop sharing my screen. All right, there we go. All right, I don't want to be there, but we'll just zoom forward. So brightness is a different thing than luminosity. Luminosity for an object's temperature isn't changing, is always the same, but brightness changes quite a bit as you get closer and closer and closer. And why does brightness decrease with distance? For the exact same reason that gravity decreases with distance. There's a certain amount of energy in the center, and that energy has to be spread out over a surface as it travels away from the center. Surfaces are areas. Area is a 2D thing. So if I am 1 light year away from the star, and then I move to be 4 light years away from the star, the ratio is 4 to 1. And knowing that it's an area, I know that that star has become 16 times dimmer. If I'm 2 light years away from a star, and I move to be 1 light year away from the star, then that star has become 4 times brighter. So brightness decreases and increases as an area. So how many times fainter would the sun appear on the planet Jupiter in comparison to the Earth? Jupiter is 5 times further out. The ratio is 5 to 1. And so Jupiter will be, think about it before you unpause the video, 25 times, or Jupiter will see the sun as being 25 times fainter. So more area practice. And I'm just going to write these problems up and then immediately answer them because y'all can pause the video at home. So from 15 away to 5 away. From 20 away to 2 away. From 1 away to 10 away, from 3 away to 9 away, from 9 away to 3 away. So ratio here, 15 and 5, that'll be 3. 3 squared is 9, and I'm moving from far away to closer, so 9 times brighter. Ratio is 10 to 1. I'm moving from far away to close. So this is 100 times brighter. From 1 to 10, I'm moving from close to far. So it's 100 times fainter. 3 to 9, I'm moving further away. And the ratio is 3 to 1, so it is 9 times fainter. And then 9 to 3, exact same thing, but I'm moving from far to close. It's 9 times brighter. For those of you who are here, any questions over this, or would you like more practice? I see no period enters. I'm going to move on. And you really are done. Here's the planet of the day. It's Mercury. I'm going to be doing a planet of the day on the slides going forward, just because I thought it'd be fun. According to the course description, this is a class about general astronomy, not focused on the solar system in particular. But hey, the solar system is fun, and these are the planets that we know the best. And every once in a while, I'll give an extra credit problem that says something like, put the planets in order from furthest from the sun to closest to the sun. I can't do it as a problem for credit because, again, this is not a class about the solar system. But these are the planets we know. Mercury has a highly eccentric orbit. It has a more eccentric orbit than Pluto does. And Pluto doesn't even count as a planet. In general, the minor planets have really eccentric orbits in comparison to the major planets. But Pluto's orbit, pretty eccentric. Excuse me, Mercury. As you know, most objects in the solar system spin counterclockwise, and pretty much all objects in the solar system orbit counterclockwise. If you're not orbiting counterclockwise, you got a problem. Because your orbit's unstable. You're going to crash into the sun. So Mercury turns this away and it orbits this way. So as you know, it moves a lot faster when it's close to the sun and a lot slower when it's far away from the sun. Given that this is the case, when it's close to the sun, it's literally going by it so fast. And its rate of spinning and its path of orbiting line up in such a way that the sun basically stands still in the sky. And that looks like this. Which is not loaded. So here's Mercury when it's far from the sun. It's getting closer and closer and closer. And that's the point at which the way the planet is turning and the rate at which it's moving around the sun are so similar that the sun stands still for a few days. Or actually, I shouldn't say days. Mercury's days are a very odd thing that we are probably not going to get into in this class. So sun stands still. It's normal speed. Sun stands still. We're back. One more time. Sun stands still in the sky. And again, sun stands still in the sky. Actually, Mercury is going around the sun so fast when it's at this point that the sun doesn't just stand still, it briefly goes backwards. Which is kind of incredible to think about. But something else that's incredible to think about is that Mercury has water in it. Probably from comets, in the craters that the sun never touches. Yes, there are parts of Mercury that are cool enough that it can have water. Mercury is the densest and most metallic system in the solar system. Maybe it used to have a more normal crust, almost certainly did, and the sun completely blasted it off over time, or maybe its crust was destroyed in a collision, much the same way as a lot of Earth's crust was stripped away when the moon was caused to come into existence by something Mars-sized hitting us. But whatever the reason, by the modern era, it looks like nothing so much as the core of the planet, not a regular planet. It has a kind of atmosphere that are comprised of parts of the planet that the sun is vaporizing. They stick around briefly before streaming off into space. It's not much of an atmosphere, needless to say. And that was it. That was it for the class. Any other questions over anything? Just turn your mic on and hit period enter.
No, I think that's everything.
All right, great. I hope everybody enjoyed the class, and I will talk to you later.
All right, thank you.